I'm really, really pleased to be here and so grateful that you guys are here to share and hear a little bit about what we've been working on at CSU. And so I think the title in itself is a little like, wonder where she's going to go with that. So I think you'll be intrigued. So I want to ask if you all recognize this painting. Does anybody recognize this painting? What is it?
It's sort of Fountain of Youth from Roanoke, this over or something like
Yes.
that. We used to have it in our living room.
Oh! He gets the door prize tonight. Yeah, well done. So yes, this is a painting from the 1500s, and it depicts the Fountain of Youth, and you can see that these older people are coming down from the village in carts and wheelbarrows, and then they are examined by a physician and a nurse, and they're invited to take a swim in the Fountain of Youth. And as they progress from left to right across the Fountain of Youth, you can see that their gray hair goes away, and their wrinkles go away, and they emerge on the other side, fresh as daisies, and they enter the tent and are dressed in finery and participate in this beautiful feast. And so what this painting shows us is that for centuries, really, people have been obsessed with this idea of preserving youth, right? And while we haven't found the Fountain of Youth, at least I haven't, it is true that we are living longer, right, as human beings. And it's really interesting to look at the lifespan of people over the many years that this has been recorded, and how lifespan began to increase as sanitation practices were beginning, and then as vaccines against infectious diseases and other modern medicines came about. And so as a result of that, we are living now much longer than we were. This is an awkward little way to turn here, so hopefully I don't bother you by that. But anyway, it's interesting to note that by the year 2050, I don't think this is news to too many people in the room, that about a quarter of the entire human race will be over the age of 65. And this is an unprecedented event in human history. In fact, the number of people under the age of 5 has diminished, and for the first time in human history, the number of people over the age of 65 outnumbers the number of people under the age of 5. So when you let your head just kind of move forward through what's going to happen as a result of that, what you realize is that a larger and larger number of people are depending on a smaller and smaller number of workers to provide services, goods, healthcare, etc. And this is a situation that we are woefully underprepared for. Now, lifespan increases is a wonder of modern medicine and practices and nutritional advances, etc. But one of the biggest problems is that it's a huge challenge, because while we are living longer, we are not living healthier. And this is that concept that many of you may be familiar with, this idea of lifespan and health span becoming uncoupled. So we are living longer, but we are not living longer healthier. We're just simply spending a larger portion of our remaining years with the burden of chronic disease. And clearly, this is not something that we want. We want to be vital into our last years of life. And so this has been one of the biggest challenges. Even though lifespan extension is a huge benefit, this is an area that we just don't have very good answers for. And if you look at the population of people over the age of 65, we know that 80% of people have at least one chronic condition associated with age. Many of us have more than one. And if we just took one example, which is dementia, you can see the increase in the number of people living with dementia that will be present by the year 2050. And our healthcare systems and social systems are not prepared to deal with this at all. This will bankrupt even the wealthiest of nations. And so we need to think about, how are we as a society and as scientists, how are we going to approach this? Well, what's fascinating to think about, if I can get this to advance, is that we actually don't die of old age. You know, you hear people say that somebody died of old age and they were just old. No, we die of diseases of old age, right? Older bodies are made up of older cells that can't heal as well as they did. And so things that a younger person would easily survive often can be the demise of an older person, because of the fact that we have lost our resilience to be able to recover from illnesses and injuries. And this is what we die of. We don't die of old age. Nothing actually dies of old age itself. And if we think about aging as sort of the common element of all of the chronic diseases that we endure as human beings, everything from cancer to stroke to heart disease to neurodegeneration, aging itself is at the center of that. And so what we do in Western medicine and modern medicine is we think about, we wait until there's a condition, we diagnose that condition, and then we do what we can to treat it. But what if instead of doing the whack-a-mole, like let's cure cancer or let's cure heart disease or let's cure diabetes, what if we were able to actually target the upstream common element that actually is leading to all of these diseases? Think about the fact that then we could impact all those diseases at one time. And that is what the area of research that I work in is attempting to do. So the core question is aging itself a condition that we can actually target and treat? And if you just observe certain populations of people, you can see that there's a well-defined interventions that actually are associated with longer life and longer health span. And they're listed here. And this is across many species, but certainly within humans, that lifelong habits of exercise are associated with healthier aging, good sleep habits, stress reduction, and interestingly, caloric restriction. So across all species that have been studied, diminishing the number of calories and not overnourishing is associated with a longer lifespan, but most importantly, a longer health span. And so this tells us that maybe aging can be changed. Maybe if we can actually, by lifelong habits, do something that changes our aging trajectory, perhaps there might be something that we can do to change aging on a cellular level. So for scientists that study aging, like myself, we need to define it, because I think if I were to ask 10 of you in this room to define aging, you probably would each have your own sort of definition or spin on that. But for the purposes of science and for my field of work, we define aging as the lifelong accumulation of damage to our bodies, i.e. our cells, that occur as an intrinsic side effect of our normal everyday living, right? It's the UV radiation that we're exposed to, it's the pollutants, it might be secondhand smoke, it might be just habits that and things that we're exposed to. And we know that living things can tolerate some damage, but if that damage is not reversed, the accumulation over time results in failure of the system, and we recognize this as a disease, or in the worst case scenario, as death, right? Total failure of the system. And so prior to last 10 years ago or so, we've always thought that aging is this inevitable thing, that it starts when you're born and it ends when you die, and there is not really much you can do along the way, except maybe have some good habits that, maintain your health. And we've thought this because we can observe aging on every level. We can look at a whole organism and tell when something is older, right? But even below the skin, you can see major changes. So this is the brain of a younger person versus an older person. So brain shrinking. This is the muscle tissue of a younger person versus an older person. We see it on a cellular level, and even down to the molecules within our DNA, we can see markers of aging down to the molecular level inside our cells. Well, this gives us things to think about in terms of how can we maybe intervene in some of these things and have a whole organism effect. But until recently, we've always thought that this was this immutable process that just keeps happening regardless of what we do. And so it'd be wonderful if we were a little bit like this old car. Okay, so this is a classic car. You can look at the car and you know that it's an older car. But this car is running perfectly well decades and decades after its expected lifespan, right? Why is that? It's because somebody has painstakingly and lovingly refurbished little parts along the way that were starting to wear out. So if aging is the common element and the greatest risk factor among all chronic diseases of later life, and if accumulation of cellular damage is responsible for aging, can we perform maintenance on ourselves or on our cells to repair damage along the way? And that is what our line of work does. So again, it's kind of like we're thinking about how can we actually lift up the hood, look under there, take things apart, tinker around, and see if we can change so that we are functioning better decades and decades after we would be expected to be declining. So that's kind of what we do. So I have two examples here And these two examples are two extremes, but they do kind of represent the variability in aging trajectory. Both of these men are 85 years of age. So they have been on the planet exactly the same amount of time. And clearly this guy, who I actually thought was photoshopped, but he has his own Instagram account. He's got this big, I think it's like ripped grandpa. I'm not kidding. I mean, clearly he's very healthy, very fit man. And then the gentleman on the right who is suffering from a greater burden of chronic age-related diseases. You can see he has mobility issues. Perhaps he's in a memory unit. He definitely has had a different pathway of aging. And yet these two people have been on the planet exactly the same period of time. So this concept of like your chronologic age or the number of birthdays you have isn't really coupled with what is going on inside of us, or what we call our biologic age, the actual age of our cells. And so chronologic age does not equal biologic age. And we see that all the time in populations. I mean, we have people that are out on the golf course 5 days a week, well into their 80s and early 90s. And then we have other people that are suffering from a higher burden of disease. And this is just what we call sort of the different or variation or many paths of aging. And so if this is the case, you would think that perhaps there might be something we could do that would change our aging trajectory. Can we actually intercede in this gentleman's life, or the gentleman with the walker, his life, to actually intercede earlier so that we can change that trajectory to be more like the very fit grandpa? And so in order to study these things, we go back to models of aging in the laboratory. And what's really fascinating about this is that the major models that we use in the laboratory are things like yeast, worms, fruit flies, and mice. So that's kind of where it all starts. And what's fascinating about these species is they have vastly different lifespan. So a yeast cell has a lifespan of hours, worms have a lifespan of weeks, flies maybe months, and mice years. And yet there are some similarities among these very, very different species that teach us a lot about what are the fundamental things that are driving aging, regardless of lifespan. And so what we have learned is that these are summarized in about 9 different hallmarks of aging, or things that we know on a cellular basis are driving aging. And whether you're a yeast cell only living for hours, or a human being living for decades and maybe even centuries, those same programs are exactly the same for the most part. The only difference between the yeast cell, so to speak, and the human is that they are playing themselves out at different rates. Well, if those same things are happening across all those species with different lifespans, those become the targets or knobs that maybe we can turn that will change the rate of aging, in our bodies, right? So think about that. That's a pretty profound set of knowledge. And so we have run with this, and many people have, not just us. And what this kind of boils down to, I think of it a little bit like a symphony. So when we are young, all the instruments are playing beautifully in concert with one another. They're making this gorgeous, beautiful piece of music. And as we age, maybe a few things start to go out of tune, but we don't really notice it at first, right? Because the rest of the instruments carry the day. Like, we can still recognize the music. It still sounds pretty good. If you're really trained, you might be able to tell that there's something a little off with the violin section or whatever. But after a while, things get more and more and more chaotic until suddenly that piece, that musical piece, is no longer recognizable. There's chaos in the system, and we recognize that as disease. And so this is sort of the analogy that these different cellular drivers of aging, that wheel, are like the different sections of instruments in the orchestra. And so we can figure out which one of these little sections of instruments are kind of off a little bit. And maybe if we can catch that early enough before there's disease, before it becomes too chaotic to recognize the music, then perhaps we have an opportunity to retune along the way. So let's go back to our two gentlemen. And now we know that this man and this man, while they may be similar in age, there's something else going on here. These cellular programs that are involved in driving aging are playing out more rapidly in this man than they are in this man. And so how do we change that? How can we make it so that this man has a better chance of being like this man? Or even at this point, can we even begin to reverse some of this damage so that they can have a longer period of time as stable place? But the problem is that we actually don't know when they diverge. All we know is that somewhere between birth and age 85, this gentleman's aging programs started playing out more rapidly for whatever reason, we don't know, than this person's aging programs. And we don't know when that happened. We don't know if that happened at birth, did it happen at age 30, at age 50? What we do know is that if we could catch it early, it'd be easier to treat, right? It'd be easier to prevent the end problem. And so we have no way of knowing that in humans. The only way I think I could even conceive of doing that is if we took blood samples from every single person from day one to the end of their life and started to look at what was changing and how rapidly that changed in relation to a different person. And of course, that would be completely impractical. It's never going to be done. So let me get this to go. So what we thought about is, okay, well, now we understand the cellular drivers. Can we actually work on blocking some of those cellular drivers so that we can prevent that change from happening? And so we go back to the lab and with all our organisms that are part of, trying to understand how some of these interventions might work. And we tried something. We tried blocking a few of these different drivers of aging with different types of pharmacology or perhaps lifestyle interventions or other things, and we see what happens. And so this has actually been done in mice. And so what we did, it's not us, this is not my work, but this has been a very famous study where they took old mice, they gave it something that blocked these drivers of aging, and they helped reverse aging or slow aging significantly. So these two mice are litter mates. They were born on exactly the same day from the same mother. They are essentially almost like identical twins of each other. The only difference, this animal was given one of those blockers of aging. This animal wasn't, and now you can see the difference as they get older. These are both old mice, but one looks much younger. And on a cellular level, that mouse is younger as well. Turns out that based on work not done by me, but by many very, very talented scientists, that aging can be modified. And by reversing or slowing cellular aging programs, we can delay the consequences of aging, this body type, on a whole organism level. Well, this was a huge, huge, huge breakthrough. And people were high-fiving in the lab. There were all these news articles. There was talk shows. And that all happened about 25 years ago. So if you're wondering why we haven't seen the miracle pill or whatever, you are not alone, okay? And this is part of the challenge in science. We call this problem the translation gap. And so what happens is a lot of discovery comes into play and people start to understand things, but what we don't do is we can't seem to get it across from where we can be very successful in the lab, we can change aging in mice, but how come we can't do it in people? Why is that? We need something that can bridge that gap. And it makes sense if you think about it, right? Because mice are not people. They live in a very controlled environment. They're not out, playing poker on Saturday nights and smoking cigars. They're not eating McDonald's. They're very controlled. So they have we can control a lot of things and they're very important for our work, but it doesn't translate to real world, right? Because people are complex. They're nothing like mice. We grow up in different environments. We have different nutritional statuses. We have different vaccine statuses. We have different socioeconomic statuses that all affect how we age. So we need a bridge across this. And this is where a lot of the aging research has been stuck for a very long time. Part of the remaining puzzle pieces are we don't have a very good model or did not have a good model that mimics human aging. And we also don't know when in humans that divergence begins. We don't know if it happens at birth, at age 10, 30, 50, 70. So let me show you two more animals. So how many people in here are dog lovers? I had a feeling maybe you might have a lot of folks okay. So we have a Jack Russell Terrier and a Great Dane. The Jack Russell Terrier is a small dog. This dog was the national flyball champion 5 or 6 years ago. This dog is 9 years old. Clearly an athlete, and this is a Great Dane. And to the practice eye, you might be able to see that this Great Dane is hunched because she's having mobility problems. She has some muscle atrophy or muscle wasting in the hind limbs. She was one of my patients, so I happen to know she also has heart disease and a single type of cancer. So this animal, same age as this animal, is suffering from a greater burden of disease than this animal, yet they are the same chronologic age. And nobody here that is familiar with dogs will be terribly surprised about that, because we know that toy breed dogs or small dogs live 3 times as long as these large and giant breed dogs. So in a lot of ways, the aging program that's playing out slower in the small breed dog than it is in the large breed dog. So this great Jack Russell Terrier is much more like this man in terms of their aging trajectory, and this is much more like the man with the walker. So why is that? Well, it turns out that big animals, usually in the animal kingdom, big animals live longer. So this is a very unique thing to dogs. Normally, like, think of the lifespan of an elephant versus a rat or chipmunk. Okay, so big animals across 99% of the animal kingdom live longer. But in the dog, this is reversed. So big dogs live much shorter. And so it has to do with body mass and size. And we know that based on our research, cellular aging programs are accelerated in large and giant breed dogs relative to those small breed dogs. But the one good thing about dogs is they age naturally alongside of us, right? I mean, they are exposed to our environments. They are exposed to our urban versus rural lifestyles, our secondhand smoke, our eating habits in many cases, our food supply, all of those things, water supply, and they have all the genetic variation, for the most part, that humans have, at least a lot more than laboratory mice. And they develop all of those diseases of aging naturally. So we're not giving them a disease of aging. That's just how they live, but they have a compressed lifespan. So they're exposed to everything that we're exposed to, but they're aging in a shorter time. And we have this divergent aging between large and small breed dogs. And it turns out that those large breed dogs do have all of these things in play at a much greater rate than the small breed dogs. But where this becomes really, really valuable is that we're in people. We don't know when 2 people begin to diverge, healthy ager, less healthy ager, but we know exactly when this happens in dogs. And it happens at maturity. So when these dogs, the Great Dane and the Jack Russell Terrier, are puppies, they age at exactly the same rate until they reach about a year of age. And then all of a sudden, the Great Dane begins to accelerate its aging relative to the young dog. So now we have a species that's exposed to everything we're exposed to, develops all the same kinds of diseases that we do in a shorter period of time, and we know exactly when they start to accelerate their aging profile and programs relative to dogs that age more slowly. So this gives us an opportunity to try interventions at known points of divergence along that aging pathway. So at 1 year of age, when they start to diverge, at 5 years of age, probably midlife, at 10 years of age, toward the end of life. So it turns out that this is the missing bridge, that these guys have been aging alongside of us all this time, and we didn't really understand the value of our best friends being part of the story. And this is kind of what we do at CSU. So I want to share with you a couple of really cool studies. So, and this is where Greg had asked me to share some more detail about this. So kind of our pipeline, if you will, would be like, yes, we do all the stuff in the laboratory animals and we make sure that it's working and that it's reasonably safe. And then if people would like to enroll their pets in these longevity trials or different interventions, they can do that. And if it works in our animal patients who are exposed to all the same things and live in our environments and all that, there's a much greater chance of working in people because it mimics human aging so much better than a laboratory mouse or even a non-human primate. Because again, they are living in our natural environments and they're exposed to all the things we're exposed to. So hopefully we can get the old Great Dane to be young or to feel young, and same with the older gentleman here. So I want to give you an example of this that is a very real life example. This is super cutting edge. I was hearing you talk about how you didn't want to talk about stuff that wasn't published. Well, I'm going to talk to you about stuff that is not published. So mum's the word, okay? Don't make it, don't ruin this for everybody. Okay. So this is a study, and this is one that I think Greg and Shanti really thought was compelling. We've known for a long time that lifelong habits of exercise protect against neurodegenerative disorders, things like different dementias such as Alzheimer's disease, et cetera. The thing that we haven't always understood is why that is. we do know that exercise does a lot of things. It releases different things in your bloodstream, and we call those things cytokines and different nucleic acids like miRNAs. But what we were really interested in is this thing, and these are called extracellular vesicles, or EVs. And we were interested in them because they are something that is small enough to cross the blood-brain barrier, and they also are very stable in your blood. So we thought, well, wonder what's going on with these little messengers in the blood before and during and after exercise. And we were particularly interested in, what was that? Okay. Oh, I thought it was something over here. No, that's great. Thank you. We were really interested in how the muscle talks to the brain. Like, if exercise is protective, like, how is that happening? How is the connection happening? What's the communication like? So what we did is we were interested in these extracellular vesicles, which are these little packets. They're nanostructures. So nano is like the size of a virus, very, very small, much smaller than a cell, very small. And they have different packets of information that are used in cell-to-cell communication. And it turns out all cells make these, but we were really interested in the things that come from the muscle, because we thought, well, that might be how the muscle is communicating with the brain, through these little messenger packets called extracellular vesicles. So what we did is we took muscle from a mouse, and we grew it in a petri dish, basically like this, and then we let them mature into what we call myocytes, or mature fibers. And you can watch these spontaneously contract. So when you grow these muscle cells in a petri dish, they will get to a place where they begin to contract all on their own without us stimulating them, which is kind of cool. I don't know, makes a cool movie. And then we took the muscle cells and we created an exercise program for them outside the body. So we actually exercised them outside the body, and then we collected those little packets of information that come off those cells that they secrete, because that's what they would be secreting into the blood. And we looked inside to see what the content of those were, if the cells were exercised versus if they just sat in the petri dish and didn't exercise. And then we compared, and it turned out, this is I'm oversimplifying, but this is the take-home message, is that those little packets of information, the EVs, collected from muscle cells that were exercised outside the body, contained factors that preserve muscle health, which one would expect, okay? But the weird thing was they had all these messages in them about brain health. And so this kind of proved our suspicion that that might be how exercise is protective to the brain, because as you exercise, the muscle cells are secreting these extra things into the bloodstream that are then getting to the brain and actually helping to protect the brain. And so this is the work of one of my PhD students. Her name is Kate Williams. She's lovely. She is just finished her thesis, and so she wrote an entire thesis on muscle health. But where we think the happy accident discovery was that we didn't expect to find all this stuff about brain health in there. So then what we did is we said, all right, well, we want to know whether we can actually enrich these little packets of information with the good stuff for the brain. And we did that. And then now we are in the process of doing this type of experiment where we have mice. Going back to the laboratory, mice that get Alzheimer's disease, basically. And we're going to treat that with these packets of information. And how we do that is through a nasal spray, because we can get these things to the brain pretty directly that way, and see if that changes the progression of their condition that is Alzheimer-like. Dogs also get an Alzheimer-like condition called canine dementia, or canine cognitive dysfunction. And so if this works in the rat and mouse, which we're in the process of those experiments now, then we will start a clinical trial in dogs with this condition, or at least mild cognitive impairment, which is kind of the early phases of that condition. And if that impacts them, then we have a much bigger opportunity to think about success in people. Because again, the dog is that model that really mimics human aging so much better than anything in the laboratory. So, is that all I put in here? Oh, here we go. So the question is, how can you help? And this isn't about donation, it's just about really spreading the word. So one is about supporting the funding of research in general. I think that's important right now. I think it's a time where that is a very strange conversation to be having. And so I hope that this kind of thing excites you and helps you be a champion for research in general, I think it's really important that we start to spread the word about the power of our companion animals, our dogs that are living with us, to accelerate aging research. We just saw how they can be a bridge that is very unique in the translation across that gap that we talked about. And then sharing your time, your connections, your talent, your treasure, whatever it is that you can help to move us forward, I think is really important. And so just kind of learning about this and gathering here today, this is about making, people aware of how important this is and how impactful this potentially can be. So I'll leave you with this. I really think that all the creatures that we do share this planet with do hold a very important role in our own health. And it's not just about the health of our animals that we eat, like our food animals and stuff. It's about the animals that live with us every day. And I do think that it's really kind of thinking about this as one medicine, that what is happening in our patients can benefit humans, but then that also translates back to our companion animals. So it's definitely a two-way street. And I think that's appropriate because I think we have a duty. I feel like I have a duty in my role that I give back. And so of all the creatures that walk the face of the earth, I do think that we have to be worthy of that gift, right? That they've chosen to be with us. So that's all I have. But I'm happy to take any questions.